this computer. Share. And then this. I think it's all yours. Oh. What just happened? This. Oh, I see what happened. It came to here. Oh my God. Seriously? Come on. Oh, look what it did. It projected here instead of there.
Oh, it's true. There.
Oh, come on. Huh. You're all set. Okay, so I don't know if you want to use this or not, but
Probably. Yeah.
it's right here for you.
It's easier.
Okay. Get started here. Not working for you?
No, it is.
Okay.
Okay. Oh, good. Well, today I get to talk about mass spectrometry, at least today, and in the next lecture, actually. It's one of the more exciting areas of analytical chemistry. I don't know if many of you find this exciting, but I do. How's that? It's what I do for my living. And we've talked about gas chromatography. Has Rem talked about LC yet? Liquid chromatography? Is that coming up? Liquid chromatography, LC? Okay, good. Both gas chromatography and liquid chromatography are pretty mature. Kind of reached the theoretical limits in them. We're not going to see wonderful changes in our ability to separate compounds in the future. We've done as good as theory says we can do. But mass spectrometry just keeps on opening up doors for us that we've never been able to open before. So I see many things happening in mass spectrometry that really will advance our abilities. So mass spectrometry, what is it used for? What does it do for us? Why do I find it fascinating? Well, we start looking at foods, an awful lot of chemicals in foods, a lot of components of foods. My area of flavors, if we look at flavor, there's over 11,000 different flavor chemicals that have been identified. Okay, if I see some peak off of GC, what is it? Which one of those 11,000? And so that's where mass spectrometry comes in. Basically, our instruments, LC, GC, just draw a line on your screen. The line means nothing. Mass spectrometry tells me what that is, what's being measured. And that's, like I say, really, really exciting. So identify known compounds, unknown compounds, elucidate the structure, chemical properties of molecules, and to quantify known compounds. It's actually a really good detector just for measuring the amount of something present. And I'll give you an example of that one a little bit later on. So when you start listing applications, it could go on for many pages. And these are just some diverse listing. Detect and quantify the use of steroids in athletes. Monitor the breath of patients by anesthesiologists. During surgery, determine the composition of molecules found in space. Determine whether honey is adulterated with corn syrup. Locate oil deposits by measuring petroleum precursors. Monitor fermentation processes. Detect dioxins in contaminated fish. Determine gene damage from environmental causes. Elemental composition of semiconductors. Determine if horses are given cobra toxins to deaden the pain in races. You know, it's not just foods, it's used so broadly throughout our analytical world. It's absolutely fascinating. Like I say, this could go on for page after page. And so what how does mass spectrometry work? What we basically do is we have three parts to the mass spectrometer. There's the source, the mass analyzer, and the detector. The source is the first part. What we're going to do is we're going to separate molecules, hopefully, put them into the mass spectrometer. And the mass spectrometer is going to, when it sees that molecule, it's going to bombard it with energy. It's going to blow it into pieces, basically blow it up. And so what will happen is that molecule will blow into pieces depending upon its structure. It'll have some strong bonds, so some pieces will hold together well. Other chemical bonds will be weak, so they will be shattered immediately, blown into bits. There'll be positively charged pieces of that molecule, negatively charged pieces, for that matter, uncharged pieces of that molecule. But basically, it blows molecules into pieces. It can't really determine what those pieces are yet, so it has to take all those pieces and separate them into each piece and then measure the size of that piece. So blow it into pieces. We're going to look primarily at just the positively charged pieces that it gets blown into, and we're going to measure them. What are the pieces? How big are they? And how much is present? So we're really going to get some pattern of bits and fragments of molecules. We detect them in a detector. So, okay, here's this molecule or this fragment. How much is there? And from there, we go into databases. That's where computers take over. And they can look at those fragments and fragmentation patterns. Oh, I know what that is. It's this molecule, so it fits. And this is, I always have to smile when I do this because especially the detector part, I ran our mass spectrometer at Penn State University for 3 years. So maintained it, operated it, and so on. At that time, which is now a long time ago, when we would take a look at the fragments, what the machine would do is it had nothing else to do, but it would draw a line on a piece of paper. So the paper would be coming out. And it would draw a line for this mass, 14, something mass 15, 16, 17, so on. It spit about 8 feet of paper out in 2 seconds. And then you'd set it out on the floor and you'd measure each of these peaks. It's like the dark ages of technology. And at that point I said, oh my God, what more could anybody ever do for us? Then computers came along and, advances sophistication. It never ceases to amaze me, like I say, where we go today. So let's look at the parts of the mass spectrometer. And so the first part is, let's say, the source. There's many different sources. By source, I mean, what's the source of energy that blows this molecule into bits? Okay. And the most common and the earliest was electron impact. And so what essentially would be done is that we would go ahead and here's our sample coming in. So a mixed, it should be a pure compound, should be coming in. Whoops, went backwards. And there's an electron beam right there. So that's where energy comes from. It can be high energy or low energy. So how much do we want to go ahead and blow that apart? And then those pieces, positively charged pieces, are going to be pulled out and go into the other sections, the mass analyzer and the detector. I'll go into them a little bit later, but here we basically have a stream of electrons, and those electrons, some of them are going to be absorbed by molecules, and they're going to blow things into bits. There's different ways we can get compounds into a mass spectrometer so we can blow them to bits and see what they are. We can actually, most instruments have a little place on the side. You can go ahead and turn a valve, pull this probe out, put your sample on it, push it back in. Now it's right in that electron beam. Electron beam hits it and measures it. That's kind of, you have to have a pure compound. It's tedious. There are places that's used. But usually we feed the mass spectrometer from a gas chromatograph or from a liquid chromatograph. The gas chromatograph, the liquid chromatograph are doing our separation, taking complex mixtures and hopefully putting one in at a time into the source, blowing them to bits and try to see what are those bits. So for gas chromatography, they're measuring volatile compounds. They're not volatile, they're not going to go in that gas through the instrument. If we look at LC, they're typically non-volatile. They don't have to be, but they usually are. Said we bombard them with energy, electrons. Those electrons will either be 70 electron volts or they'll be 20 electron volts. And I'll explain why we might use one versus the other. Many of our chemical bonds, our good, strong covalent bonds, only are about 10 electron volts. So when we hit it with 70, like say, it's like putting a bomb in there, it just blows it to pieces. So we hit it with energy. There are different terms that we'll use here and certainly in the field. We'll talk about a parent ion. That is that bit in pieces. That is the molecular weight of your compound. So it didn't fragment at all. It just picked up a charge. Oh, great. And so that's the molecular weight of the compound. Sometimes you don't see them because that molecule is too fragile. Sometimes you do. The base peak is actually the most abundant fragment that we just formed. So what we do when we quantify, okay, this is the most abundant fragment. Oh, this other fragment, oh, that's only 80% of that. Here's another fragment, 60%. So they're based on each fragment, the amount present, is tabulated based on the most abundant peak. And that's what goes into your library. That's what the computer deals with. It looks at the molecular weight of that fragment and the amount of that fragment. An example here is chloroacetylphenone. That's in the center of the diagram. So they've got two benzene rings, carbonyl group in the center. That is the parent compound. It has a mass of 216 molecular weight. And so here's our chart. So that's a fragment at molecular weight 50. And so 50 to 100, 100, 150, and so on. So see 105. 105 is the base peak. That's the most abundant fragment that we have in this chromatogram. So here's our molecule. Just picks up positive charge. We get a mass of 216. One of the fragments that it's going to break into is in the upper right-hand corner. That's a mass 139. You can see where it comes from. It broke the bond. It's a molecular weight 139, and there's your peak at 139 that's been measured. So these are the most abundant pieces that molecule break into. So it gives us a pattern. What's the molecular weight? How much of that piece has been formed? I said we have either 70 or 20 electron volts. That's how much energy we hit each molecule with. The advantage of high energy, that breaks a lot of bonds, we get a lot of pieces. If we got a lot of pieces, we can kind of put a puzzle together. And so we gain more information about structure, about what the molecule is. The problem is, we like to see molecular weight. We like to see that parent ion. I like to know it's a mass of 216. I know it's a mass of 216. It eliminates an awful lot of compounds in the universe. So having that, the parent ion there is really, really useful. But oftentimes that's so much energy, it blew everything apart. There was nothing that stayed together. There was no parent ion. And so we're going to not get, we're going to get a lot of fragments, none of them very abundant. But our choice is to use the low energy, the 20 electron volts. If we do that, then we don't blow into so many pieces. We really stand a good chance of seeing the molecular weight. Like I say, I'd like to have that molecular weight. Also, we're measuring only one peak or less peaks. If we measure less peaks, they will be bigger. And so they're easier to see. So this is just looking at the spectrum of pentobarbital. And so pentobarbital, if we use the high energy bombardment, we're going to go ahead and find no parent ion. The mass should be 226. There might be a little bit here, maybe not. So we're going to see fragments here that blew it into smaller pieces. If we go ahead and use that lower energy, we're going to get the molecular weight over here, and we're going to get less fragments to look at. So there's pros and cons. The low energy gives us a molecular weight. The high energy gives us more pieces to look at structure. So they both serve their purpose. Now that's electron impact. That was kind of the first source that came along to blow molecules up. And since then, we've added many new techniques. MALDI, matrix-assisted laser desorption ionization. ESI, Electrospray, that's the one that your advisor instructor loves the most, because that's most commonly interfaced with liquid chromatography. We have DESI, direct electrospray. I'm going to show you a quick picture of each of these, but okay, so I don't need to read them. You can read them. So there's many different ways that you can blow these things apart, basically put energy into that molecule. The MALDI process is really good for high molecular weight compounds. By high molecular weight, I'm thinking maybe 5,000 to 40,000, something in that ballpark. So if you have large molecules, it's really, really good. High molecular weight, proteins, peptides, glycoproteins, oligosaccharides. It'd be terrible for me. I work with flavor. I work with things that are volatile. I would never use this kind of detector. And so, but I do use it in a different way. I'm interested in how flavors interact with proteins. They will chemically react with proteins in your food. I try to flavor it so it tastes good, and those chemicals don't react with the protein, the flavor goes away. So what I do is I use this technique. I can see my protein, and I'll give you an example a little later. So I see the mass of the protein, and oh, I see the mass of protein plus my flavor compound. My flavor compound's been added on, two flavor compounds. So it's a nice technique for looking at, let's say, larger molecular weight compounds. How's that done? How is MALDI done? Sample is pre-mixed with a high energy absorbing matrix. So it's put in a matrix, loves to absorb energy. So it's hit with a laser beam. So we actually hit that matrix. The matrix basically picks up the energy, transfers it to the molecules I'm looking at. So it's kind of a handoff. Let's go ahead and let's say energize that matrix, pass it on to our molecules. We don't get a lot of fragmentation. It's really a low energy transport. And so we're usually just going to get the parent ion. That's all you're going to get. So that's not great if I want to know what it is, but it's really good if I want to measure that compound. I want to keep track of that particular compound. And this is hit with a nitrogen laser, 337 nanometers is the energy. And this is kind of shows the process as it goes along. And so here's our matrix in purple. We've got the energy coming in from the laser. Likes to get ahead of me. So we've got energy going in. We draw those fragments out. There's going to be pieces that have a positive charge. Draw them out, and we're going to take them down to a detector. So like I say, a fairly simple, convenient, easy to run methodology. It's what we call a soft ionization, low energy. And so we don't get much fragmentation. So it's easily interpreting the data. And actually, each molecule of protein, if we're measuring protein, picks up one charge, only one electrical charge. And that makes it easier if I start measuring what's the charge and mass that I'm looking at. So it's really easy to interpret and very sensitive. The only problem that we have is it is limited in molecular weight. So to measure any of these molecules and fragments, I got to get them into a stream. A stream, it's a vacuum, but I need to have them moving. And a protein's a big molecule. I have trouble getting that darn thing moving if I've only got a one electrical charge on it. And so I'm limited in mass. I can't do very, very large proteins. So I have to use, again, a different technique that puts multiple charges, but it's a beautiful technique, simple technique. You get nice data from it if you're not getting too big or too small, kind of mid-range. This is an example of a protein. What's its mass? It's hard to read here. 3,000 something? Oh, it's easy to read up there, isn't it? Okay. So it's a protein has a mass of fairly low protein. I'm sorry, low molecular weight protein. But very nice. One charge, there's one peak. Easy to measure. Yep.
Isn't that the M by V though? Isn't that the mass by charge?
Yep. Yep. It's a mass per.
If the protein picks up multiple charges, that's why you would get a lower M.
So this technique only puts one charge on. It doesn't put multiple charges. So
This must be a peptide, right?
it'd be a peptide.
Yeah.
And so, it's fairly slow, low molecular weight, 2,000 molecular weight. So one mass per unit charge. There's other ways to do this, fast atom bombardment. Well, instead of hitting some matrix with a laser, let's go ahead and hit something, a matrix, with a different energy source, that's all. Instead of, like, say, a laser, we're going to take argon or xenon. We're going to energize them and we're going to bombard our sample with just a different energy source. Particle beam, so we're actually hitting xenon or argon, we're hitting this matrix. Again, what we do is we transfer energy over to our molecules, and we then, of course, analyze them. And so this is just a picture of what we would see for there we go. I'll get back there. And so this would be our matrix sitting there in kind of the orange and hitting with the atomic beam. Going to break into positive, negative charges. We're going to draw out only the positive charges and we're going to focus them into our mass spectrometer. So very simple technique for looking again at these types of molecules. I keep on going the wrong direction, up and down. I can figure that out. But anyway, so this is a different source, a different way of hitting something with energy. And this is what we call DESI, direct electrospray ionization. And so in this case, we've got solvent coming in from your top left. That solvent is going to be put under a very high electrical current. That solvent will become energized and we can direct it towards the surface and it will hit the surface, it'll energize, it'll fragment some things on that surface, they'll be bounced off and then drawn in to a detector on the other side. And so it's a real simple technique in this sense. So let's say we want to look at an apple. I gave an example in gas chromatography at looking at residues on apples, fungicides, herbicides, not herbicides, fungicides. And so one simple way, instead of doing what I did last time, soaking it in a solvent and doing gas chromatography, why don't I just take my apple, hold it there, bombard it with high energy source, collect the ions and fragment, and get a determination. I can see what's on that surface. Anybody ever gone to an airport? Ever gone through security? Did they ever take your luggage and swab it? and put it under a machine. What did they put it under? They put it under a DART mass spectrometer. It looked at that swab for obviously bomb components. And so this is just a different way to ionize. It's more or less of a dry interface. The other had a solvent spring on it. This is now where we use a high energy source in a gas phase. And so that hits your sample and bounces off and gives you a determination of the surface composition. This is the Electrospray. Like I say, that's the workhorse of liquid chromatography. In this case, you got your sample solution coming in that can come in from a liquid chromatograph, so on our left. But where the sample enters the MS section, there's that tube that comes in, has a potential of about 4,000 volts, so high energy. It sprays that solvent into a spray, but it's under a vacuum too. So that solvent is volatile. The solvent tends to just evaporate and it leaves the ions that you want, the fragments of what you're measuring. That goes into your mass analyzer and basically gets separated into fragments, and the fragments are measured. So it's a nice way, because liquid chromatography, there's a fairly high volume of solvent. You couldn't simply dump that into a mass spectrometer. Could never pump out all that solvent. So our whole purpose here is to get rid of that solvent and ionize the fragments of the molecule. So it's like I say, it's really the workhorse. The problem with electrospray ionization, or I don't know if I'd say it's a problem, maybe it's a blessing too, is that you're going to be able to, or you're going to have numerous charges per each molecule. MALDI did 1 charge per fragment molecule. This may put 1, 2, 3, 4, 5, 10 charges, 15 charges on it. And so you're committed, when you start separating fragments, you've got really a mess to try and straighten out. It isn't 1 fragment with 1 charge. I got 1 fragment with many, many different charges, and that really complicates it. So interpretation gets to be much, much more of a challenge. But the nice thing about it is, like I said, I have to make this fragment volatile. I've got to get it through my mass spectrometer. How do I do that? Well, the idea of having a charge, maybe 10 positively charges, it's easier to draw out. I can draw it up into your inlet to the mass spectrometer much easier if it has more electrical charges. So it's not limited in mass in the same way. If you want a bottom line statement, how's that? It's not limited in mass as much as MALDI. So MALDI does lower molecular weights. Electrospray does much higher molecular weights for analysis. And so again, thanks to the blessing of computers, the computer can kind of sort out, oh, this is 1 charge fragment. Oh, that's that same fragment with 2 charges, same fragment with 3 charges, and adds them all together to give you 1 turn. What's that? When would you want something other than the base peak? Well, you're going to have to put something together. You're going to get fragments. And if you only get 1 fragment, where did it come from? You want a range of fragments. You can say, oh, okay, I see. This is part of the molecule. Oh, here's another part of the molecule. You can start putting those fragments together. So you want more than just the parent, you know, the molecular weight, and you want more than just the most abundant. At least for identifications, let's put it that way. So, okay, we're blowing this molecule into bits. We're putting an electrical charge on it one way or another, so positive electrical charge. Well, we've got to now separate all these fragments that we just blew this thing into. We've got to be able to measure each fragment 1 by 1 and say how much of each of these fragments. So we've got to have some kind of way of separating these fragments so we can measure them. And that's kind of what the mass analyzer does. The mass analyzer takes those fragments, bits and pieces, and separates them so we can measure them. There's different techniques. Magnetic sector, that was the first, well, first or second type of mass analyzer that was developed. Quadrupole came in and become extremely popular. Ion trap has found some use. Time of flight is really now the preferred methodology. And I'll go through just briefly these so you know what they are, have an idea. I put a question down there because, okay, what's next? Like I say, the innovation is just marvelous in this field. So this is, like I say, one of the first types of mass analyzers. So on the red portion over there, you find that's your source. So let's blow this thing into bits. We're going to draw them out. They're all positive. So there's basically an electrical charge here. So all these positive parts get drawn out towards the negative, and they get focused and cut in the beam. So right now, this is a complete mixture of all my bits and fragments. Now, if I put that into a magnetic field, there's somewhere around here a right-hand thumb rule that says an electrical charge moving through a magnetic field will have a force exerted in this direction. And so that magnet has a very low current originally when we start the process, and then that focuses your lowest molecular weight mass around the curve. Bigger, heavier ones just smash into the end. So a little bit of magnetic current there. The first masses, small masses go, then I start more current, more current, more current to the magnet, bigger and bigger magnetic fields. So maybe our first sample, it's things of 15 molecular weight. Okay, a little more magnet. Now I'm focusing things with 30 molecular weight and 100 and 1,000 and 10,000. So by changing magnetic fields, you can focus different mass to charge ratios around this curve to be detected. Say that was one of the earliest types of detectors. The problem is the magnet weighs about 400 pounds. It is a challenge to bring up, to power up quickly, release the magnetic field and start all over again. So it has some disadvantages of real fast responses. And it's really cumbersome. You don't have it in your lab very easily. This is a second type, and this is now the mass analyzer. And so what we've got here is we do exactly the same thing. We bombard our sample, we get an electrical charge, we draw through a current to extract it out, and we've now got all of these masses flying out. But somewhere in physics, so I hope you remembered, kinetic energy is 1/2 mv squared. V squared is a velocity. So all of your ions have the same energy, but they all have different masses. They have different masses. Each of those bits and pieces are traveling at different speeds. So I've got a tube that's maybe that long, bombard it, fraction of a second, and then draw them out. And now there's kind of the race going down there. The smallest ones get to the detector first. Oh, I measure them. And then the bigger ones and bigger and bigger and bigger and bigger. And you do it all over again. The ability to monitor nanoseconds, it permits this to be really, really accurate. So simple detector, and now, like I say, the workhorse in the industry. Quadrupole was for a while. In this case, the stream of charged fragments goes down between 4 electrical poles, and they're balanced in fields, strengths and fields and alternating circuits, such that as it shows up on the upper right-hand side, a mass of 100 under this condition would have actually made it between these poles and got down the detector. The mass of 10, smaller masses, just they're not focused. They're going to be completely absorbed. Bigger masses, so we're down to 1,000, they again don't make it. So you use those 4 electrical poles to balance that field, to make charged ions traverse down between those poles. That was really popular, not because it's a fantastic detector, because it's cheap. How's that? It took mass spectrometry out of the $500,000 category down to, oh, $150,000. So a workhorse, I think we've got 3 or 4 up in my laboratory that are based on this principle. The ion trap is just another way to separate, again, these fragments. And so it's a much more complicated mathematically, but it has the ability to take these charged fragments and kind of collect them. So you can say, hey, I want to collect a certain fragment, a certain mass. You can set it up so it collects that mass, but it's going to collect it from the gas chromatograph and keep on pooling it, and then release it and measure it. In my other instruments, it's whatever's coming through. I get a response. In this one, it keeps on collecting, and then releases so I can measure it. Basically, its advantage is sensitivity. It stores up ions over some time, so it can pool those ions and give you an accurate measurement. So they have their primary advantage, like I say, in terms of sensitivity. That's a number 1, let's say. Now, what makes mass spectrometry so great is that we're actually have a wonderful detector. We're detecting electrical charges. Electrical charges are easy to amplify. So that's just amplifying electrical currents. Hey, we've been doing that for a long time. We can do it really well. So when an electron hits this first, let's see if I can, here we go. So here's our charged fragment. That's a positively charged fragment. It's focused on this first plate. That first plate has also an electrical charge. So 1 ion hits there, it liberates 100 ions that goes on to be focused to the next plate. And those 100 get transferred, magnified into 1,000, 10,000, 100,000. So every time it goes through, we can magnify it. We can't do that with any of our other detectors. So that's what gives us tremendous sensitivity to this instrument. So it gives you specificity, it gives you sensitivity. Data interpretation is always interesting. This is kind of a real simple example. And so what are we looking at? We're looking at acetone, 3 carbons, 2 methyl groups, and a carbonyl in between. So its molecular weight is 56. Is that 56? 58. 56. Whatever's on the far. 58, okay. And so its mass is 58. I put it into a mass spectrometer, blows it into bits. These are the bits it blows that mass of 58 into. There's some, just what we call the parentine over there. Yep, we're measuring it. There's some mass 58, that's nice. But okay, it can also, one of those fragments will be just ripping off methanol and tossing methanol out to be measured over here. So again, a fragment there. And so it'll keep on losing pieces. And so we can see all the parts or all the fragments of that molecule. And like I say, we put those together. And so that's really simple if it's only 3 carbons. If it happens to be 20,000 molecular weight, you can see we're in an awful lot of fragments and some really good challenges. I think I've got a slide here, yeah, that comes up. So I'll get back to that. But this is really, really neat, because what's happened is that for a long time, we could only have things to the nearest mass unit. We get a mass of 58. Oh, is that 58.0417? That's composed of these particular atoms? You don't know, we didn't know. Now, we have such accuracy and timing on the time of flight instruments that we get an exact mass. And so this is just giving you an example. What's the molecular weight of nitrogen? About 28, right? What's the molecular weight of CO, carbon monoxide? It's about 28. A low resolution instrument, our normal instruments, would say 28 for both of those. But the high resolution instrument says, that's not 28, that's 27.995. oh, that can only come from one carbon and one oxygen. Over there, we got 28.005 for our other 28 peak. That can only come from two nitrogens. And so high resolution has given us elemental information. What are the atoms that have been put together to give you that mass? So another really strong, powerful part of this instrument is to have exact mass elemental composition. It doesn't tell you necessarily, if that doesn't tell you how those pieces got put together, but it tells you what those pieces are from an elemental standpoint. We do have, like I say, good computer searching capabilities. Let's take all those fragments and let's go to libraries and look them up. I always say use care in that because machines can do some things really well, but they're not too bright. And so they may give you some identity that isn't correct. It's the best we can do. Okay. So I don't know. It's going to be, machine will tell you it's probably this, it could be that, or it could be that in some cases. It takes a little bit of finesse in there. And so what I always tell my students, what machine says it's that, good, that's a good starting point, but you need to validate that. You need to use other techniques to be absolutely certain that is the compound the machine says. I went to American Chemical Society meeting and the fellow was looking at pineapple flavor. He was telling what are the aroma components in pineapple that make it smell like pineapple. And he's, back in those days, it was really unique. And so they would just have long lists. Oh, okay, here's the 300 compounds that are found in pineapple. It's really boring. Listen to going through 300 compounds. Okay. But he started off and he said, okay, this compound is this is normal butanol, this is now ethylbutyrate, this is some ketone, and here's normal butanol, and he goes on. I say, wait a minute, you can't have butanol in two places. There's no isomers of normal butanol. And so I asked him how he was identifying. Oh, he said he took what the machine said. He didn't think about it. He should have said, you can't have the same molecule, coming out of a gas chromatograph here and here. It's impossible. And yet he was presenting it as gospel, as, being true, which is really, really fascinating. You got to use care. You always have to use care in accepting it. I never accept it. I say it's a really good starting point. If it's really good data, it's a really good starting point. But it is never final until you use other techniques to confirm it. So at this point, the idea, we've got a source, we have a way to give us our fragments, got a way to separate those fragments into one by one, we've got a way to detect them. So, okay, that's a mass spectrometer. But as I said, we really tend to interface them with other instruments because the instrument isn't really happy if I give it a mixture. I give a mass spectrometer. There are cases where it can take that mixture apart and tell you what's in it, but oftentimes it can't tell you that. And so what we do is we use gas chromatography or HPLC to separate our mixture. Now I'm getting one component, compound coming off at a time. We bombard it. Oh, that's what that is. Oh, here's the next one that comes off. So we depend upon HPLC or GC to do our separation first. So that's feeding our mass spectrometer. The biggest problem we run into is that mass spectrometer has to run under a vacuum where all these ions are formed and they're traveling along through a flight tube or through some source. It has to be a high vacuum. If there's any air in there, your fragments hit air, they get neutralized and they're gone. So we have to run 10 to minus 5th millimeters of mercury to be able to have the kind of environment that these ions will survive. So we have to have a high vacuum system. And so if we look at gas chromatography, I have a mobile phase, right? I have a gas coming off my gas chromatograph that's being put into the mass spectrometer. How do I manage that? How do I tend to get rid of that gas? In gas chromatography, and so there's your GC, and there's the interface and analyzer. In gas chromatography now, our columns, have you all had the GC lab on fatty acids? Okay. So you should have seen that column. That's a tiny column, really tiny column. And your flow rates of that mobile phase, your carrier gas, is really very low. So that's maybe 1-2 mils per minute. And so that's, our mass specs have big enough pumping systems that they can manage 1 or 2 mils per minute. And so we'll kind of skip these pumps. So that one, let's say it's 1 mil per minute, it can manage that, the pumps can manage that. You have to keep in mind though, 1 milliliter of gas coming into this high vacuum changes into 10 to the 6th milliliters of gas under such high vacuum. So those pumps have a good job to do. They got to pump out 10 to the 6 milliliters of gas per minute to be interfaced with the GC. When you're, well, and this is just basically showing the system, a column going into a quadrupole mass spec. I'm going to take a diversion that I probably will bring us up to quitting time. It's to show one of the strengths of this system when it's combined with a gas chromatograph. If you look on the upper left-hand corner, you've got an orange tracing, an orange chromatogram. And so that's basically a sample. It's a sample of paint. And so paint composed of all kinds of different chemicals. So our GC is trying to separate the paint components into one component at a time. Here's one component of the paint, a second one, and so on. So we've got our trace coming along. Now, that is a really complex system. And so we don't have any guarantee that our instrument really did separate into one by one. So, okay. And that's what's right above, the section right above that orange part, where it shows, there we go. So up here, here's the orange part. But the green, the kind of bluish, and the purple, they are all other components. That peak that you see that goes like that, looks kind of nice, are actually made up of 3 things. They're not made up of one thing, but collectively they add up to the orange one. And if you don't think about this very much, you might say, oh, there's that peak. Oh, that looks really nice. We'll measure it. And that's what it is. We'll pick the most abundant thing in there. We'll say that's what it is. When in fact, there's 3 things under that middle peak. The diagram off to its right over there kind of only focuses on 2 of those 3 components. It's left out that smaller third one along here. But what the mass spectrometer can do is that these peaks will not actually be perfectly aligned with each other. There might be nanoseconds different in elution time out of gas chromatograph. The gas chromatograph can't manage that, but the mass spectrometer can. The mass spectrometer gets a fragment of all this mixture of fragments. Okay, the sum of the 2, right? But they're offset a little bit in time. It could be nanoseconds different between one set of fragments moving like that and another set moving with it. And so the mass spectrometer can look at different sets moving at the same time, and it can treat them separately. It can identify them separately. And so when you see peak 37 and 38 over there, the green ones, the fragments 69 and 111, they're coming from one component of that mixture. The 57, 83, 99 are coming from the other components. So the machine can say, oh, these fragments are moving together. That fits this particular compound, which is a cyclohexane on the left. And the other fragments, oh, that fits another compound. So again, that detector, that mass spectrometer, can separate components that are separated only by nanoseconds that we'll never see in our usual instruments. So it's an extremely powerful tool when we put it into a detectoring system. Well, we got seconds left before we, right? Yep. It's Friday, right? Yeah. So if a minute early is okay?
30 seconds?
Yeah, let's give you 30-second break. Anyway.
Before you leave, everybody, just a quick comment. Gary updated his MS lecture a little bit, so if you have the slides in a book that you purchased, please refer to Canvas. I've uploaded Gary's slides there under week 6 materials and under week 7 for Monday materials. Okay? Thank you. Have a great weekend.
You live up that extra time.
Yeah.
Okay, I'm home, walk the dogs.
All right. Enjoy. We have PNT.
Have a nice weekend.
You too.